Assalamualaikum everyone. Today our group will present power flow analysis of a 110 kV power supply system for course BELK3393. This study focus on how power is distributed across the grid and ensure the system operate with its safety limit. This project was complete by our team, Muhammad Nuraiman, Muhammad Firdaus, Muhammad Ilyasa, Muhammad Suban, and me, Muhammad Syamil Hakimi. Power flow and short circuit analysis are first of power engineering by analyzing magnet, turbine, and current. We can measure the strength and stability of the network, which is vital of technology advance and system reliability. Now, let's look at the system architecture. We have a total of 11 sorry we have a total 11 bus. Okay, the generator, there are 4 generator, G1 to G4. G2 serve of our balance or slack machine. Our voltage level generation at uh, 13.8 kV and 16.5 kV. This is step up via 4 transformer to a transmission voltage of 115 kV. Okay, for the load, the power is delivered to 4 main load center located at bus 3, 4, 8, and 9. This is the figure 1 writing diagram. It illustrates the physical layout of our grid. You can see the step-up transformer connecting the generation buses to the high voltage transmission network, creating a robust ring main style topology to ensure power can flow multiply path. Finally, looking at figure 2, our simulation results show a healthy system. Voltage profile. Most buses are maintaining a steady voltage between 0.90 pu and 1.04. For the line loading, the percentage showing in the blue circle indicate line capacity used. For example, the line between bus 9 and 11 is at 49% capacity, while other are even lower, meaning there is no risk of overheating or overloading. Okay, for the flow, we can access the MW and MVAR value moving from the generator to meet the specific demand for each load bus efficiency. Okay, thank you. That's all for me.
Assalamualaikum, my name is Muhammad Suban Rosman. Today, I would like to talk about power flow analysis. Summary table 1. The table 1 represents the bus node status. Purpose shows the health of voltage at each substation. The key point is all voltage are within the safe range of 0.95 power per unit to 1.05 per unit. Lowest voltage found at bus 4, which is 0.953 per unit, due to the high load at that location. Phase angle. The largest angle is at bus 4, negative 10.1770 degrees, showing it is the point furthest from the power source. The slide 2 is showing that table 2 generators. generators data. The purpose of table is shows how much power each plant is producing. The key point is total active power produced by 4 generators is 573.43 megawatt. Generator 2 at bus 5 set as the slack bus to balance the system and cover power losses. All units use average use AVR, which is automatic voltage regulator, to keep the voltage stable. The table 3 shows the load data. The purpose is shows the electricity consumption by cities or industries. The key point is the total demand is 565 megawatt, which is active power, and 173 MVAR reactive power. Bus 9 is the heaviest load center, consuming 157 megawatt. So we're going next to table 4, which is branches, input line and transformer record. Table 4, branch input line and transformer data. The purpose shows the physical properties of the cables and transformers. The key point include resistance and reactance values for every line. All lines have a safety limit A of 250 MVA. Transformers are used at bus 1, bus 5, bus 7, and bus 10 to step up or step down the voltage. So we are going to table 5 data, which is branch, state, line, and transformer record. Table 5. The purpose is shows how busy the cables are and how much energy is lost. The key point is highest loading the line from bus 5 to bus 6 is the buses at 78.9% capacity. Active power loss megawatt very low, only 8 megawatt because the cable resistance is small. Reactive power loss MVAR very high, 71 MVAR. The reason is this happens because the cable reactance X is much higher than the resistance R, consuming a lot of reactive power during transmission. Thank you. That's all from me. Thank you.
Okay, Assalamualaikum. My name is Muhammad Nuraiman bin Muhammad Hasim, and my matrix number is B11231018. So next, currently on screen we can see our 11 bus system in its starting stage. We already input all the generators capacitance like 150 megawatt here at Gen 1 and the load demand through the system. However, if we look at the transmission line and transformer line, we can see 0% indicator. This means the power flow has been calculated yet. The system is just prime and ready. So now I will simulate. Immediately we can see the change, the transmission line now how show the percentage load. For example, line 1 is 70% and line 7 is 15%. Also note the generator power output, the MVR has been adjust to the meet system demand. Currently there are no red line anywhere on the diagram, indicate that no component are overload. The system is healthy. The simulation looks good, but we can just trust the software binding. We need to verify this result with a manual calculation. To do this, we are start with basic voltage conversion as shown here. The formula is straightforward. The actual kilovolt kilo kV equal the per unit voltage multiplied by the base voltage. For example, at bus 1, multiply the 1.025 per unit by our 13.8 kilovolt. Base give us exactly 14.145 kilovolt. So next, the move to more complex power flow calculation. This side detail how we calculate the flow from bus 2 to bus 3. So this is the calculation number, but the process involves take the voltage data from the table, calculate the current flow between the bus, and finally determine the complex power. Once convert from per unit to real value, our manual calculation yielded 38.08 megawatt of active power and 17.02 MVAR of reactive power for this specific line. Next, once we had our manual calculation complete for various part of the system, we compare the side by side with the simulation data. This table show the comparative analysis for both active and reactive power. The key thing to look at here are the error column. As you can, we see the different near level, practically zero into almost every case. This confirm that our manual maths lie perfectly with the simulation physics engineer. So next, finally, we perform the same comparison for the bus voltage through the network. Result here we even more precise if we look at the error column on the far right. The maximum record discrepancy across the entire system was only 0.01 kilovolt. This extremely small margin of error successfully validate our model. We are confident that the simulation is accurate and ready for future system analysis. So that's concern my part of the presentation. Thank you.
Assalamualaikum and good morning. Today I will present short circuit of our assignment. So this is data for bus 1, 2, 3, 4 and 5. So each each bus has fault current. So the first one 6.375 for bus 1 and 6.965 for bus 2, 6.321 for bus 3, 6.293 for bus 4 and lastly 6.032 for bus 5. The maximum fault level at bus 2 which is the highest fault current at 6.965 and the minimum at bus 5 which is 6.032. Total fault current at each bus is the sum of contribution from generator, transformer and line. Their value are essential for circuit breaker sizing and protection relay setting to ensure system safety. Next, this is the continuous of our data uh, from bus 6 to 11. So each fault current was 6.866 at bus 6, 5.899 at bus 7, 7.212 at bus 8, 7.065 at bus 9, 5.257 at bus 10, and
170 at bus 11. For every node, we have listed the reference value and the specific connection. This data is essential for us to monitor the load distribution and identify any inconsistent or fault with, within the circuit system. That's all from me. Thank you.
Assalamualaikum and hi, my name is Muhammad Ilyas Habib Ahmad Kamil, B112310482. Today I will present you about the data short circuit. Okay, this is the result of our circuit. So the table shows the per unit bus voltage magnitude during the fault. Okay, as we can see, the voltage at the fault bus drop to zero represented by the diagonal zero in the table. The other values show how the voltage dips up or drop across the rest of the system. Basically, the closer a bus to the fault, the more its voltage drops. Okay, next slide. Okay, for legal or regulatory compliance, we follow the governing law that is the electricity supply at 1990 at 447. The regulatory is the ST, Energy Commission, or as known as the Suruhanjaya Tenaga. Okay, these are the Malaysian grid code standard. So the voltage limit is within below negative 5% to positive 10%. That is normal, while the contingency is around plus minus 10%. For the short circuit limits, uh, the the actual value of our Malaysian standard is 132 kV. System must not exceed 31.5 kA for 3 seconds. So the frequency is the same for all entire country. That is 50 hertz plus minus 1%, and the power factor is minimum 0.9 for high voltage connection. Okay, for the societal and cultural consideration, for the economic stability, is preventing blackout like South Australia or Brazil cases avoid massive economic losses to the society. We need to prevent those to reduce our maintenance cost and money loss. Okay, second, public safety. Short circuit study ensure that Malaysia's substation remains safe and do not cause fire or explosion. We can help to reduce uh, our inflammation and damage. Second, and third, consumer benefit. OPF study help retailer maintain lower electricity tariff by optimizing generation cost. Because the bigger the country, the higher the demand for less lower is it just electricity bills. Okay, lastly, environment. Lazy power losses help reduce the carbon footprint for the grid for the electrical grid. That's all from me and us for the presentation. Thank you.